I'm Taylor Witcher, and I'm going to talk about immobile elements trapped as precipitants in fractured magma. The context of my research comes from the fundamental question, how do metals leave magma bodies to later form ore deposits? The schematic on the left shows an example of an ore-forming system. Most of these processes are well understood. We know magma ascends from the bottom and differentiates. We know metals somehow exsolve from the magma, and we know fluids transport those metals up into the crust to form into veins, etc. But this little part here where the metals leave the magma, it's not clear exactly how this happens. There are two main hypotheses. One is that external fluids come in contact with magma and transport elements away. For this scenario, high permeability is required surrounding the magma body, and hydrothermal alteration is a result. The second is that elements are carried directly by degassing fluids into bubbles or fractures. If no permeable system exists between the magma and the host rock, the elements are trapped as the magma solidifies. We're going to focus on this hypothesis. Our area of study is the Sandfell laccolith, located in eastern Iceland. It's an exposed microcrystalline rhyolite magma chamber emplaced at shallow depth with a preserved fracture system that formed during emplacement, as described in Matson et al. 2018. The system is comprised of bands of parallel centimeter-scale tensile fractures, the arrows are pointing at them here, and they're separated by dense impermeable rock. At least 1/3 of the magma volume contains these fracture bands in abundance. But it's worth noting that fracture bands are not unique to Sandfell. They've been found in many other contexts, such as obsidian flow bands, a rhyolite lava, a welded ignimbrite in contact with a dike, and a crystalline trachyandesite. These features are easily overprinted, so we think they're common during emplacement but difficult to preserve. From Sandfell, we took a bunch of samples of the fracture bands to make thin sections, and immediately noticed the light-colored halos around each fracture on a fresh surface. These halos are not visible in thin section. All we see here are wobbly, jigsaw-fit walls and irregular oxide fillings. In SEM, the fillings become a lot more complex. Iron magnesium oxide lines the fracture walls, as well as lanthanum oxide in bright white. Manganese carbonate bridges the gap, and a clastic reworking texture is found at a lot of the tips. The tips themselves are blunt and irregular, and sort of diffuse into a higher porosity zone of the ground mass. On the other side of the same crack, there are more examples of different growth textures. This indicates a very dynamic setting of precipitation inside one fracture alone. In a different sample, we see the same iron magnesium growing in the fracture and in the pores surrounding the fracture. And in this case, it also has a good example of the clastic reworking texture, where you can see bits of iron and carbonate and ground mass rounded and smashed together. Also worth noting is this early stage fracture forming underneath, and the fracture is forming by segments joining and avoiding larger microcrysts, and within this tiny crack there's even iron precipitating. So this tells us that formation and precipitation are happening simultaneously. A general stratigraphy was observed in all the thin sections. First to precipitate was the iron, magnesium, and rare earth elements in white. Next came the carbonates that bridged the gap, and finally the reworked texture pushed into the tips. We CT scanned the thin section blocks to see how the fillings look throughout the sample. On the right is the thin section view, and on the left is the cross section. The grayscale is the same as before, with heavy elements in lighter grays lining the walls and tips, carbonates and bits of ground mass filling in the bulk of the fractures in a medium gray, and black is pore space. From these scans, we calculated only 20% of the fractures are open, 80% of their volume is filled. Furthermore, these colors represent connectivity between the phases. Only 1 to 3 main fractures are communicating with each other, likely through these smaller oblique fractures that join them throughout the sample. This suggests a very low permeability in the entire system. We did a chemical analysis through energy dispersive X-ray spectroscopy and micro X-ray fluorescence. Here's an EDS distribution map of silica, showing no strong changes in abundance except for a finer grain size at the tips and coarser grained aggregates within the fracture band. The fillings, however, show a clear enrichment in iron, magnesium, and manganese compared to the ground mass. Micro-XRF heat maps show strong enrichment in the fillings of manganese, titanium, barium, and zinc, as well as the rare earths lanthanum, cerium, and yttrium. Previous studies show that rare earths are most easily transported in fluids whose conditions would have altered the surrounding rock much more than what we observe, so these enrichments are particularly interesting. The only element to reflect the alteration halos we did see in hand sample is iron, when we dropped the heat map scale to 25%. To quantify this change, we took high-resolution micro-XRF measurements on polygons in each region. The blue data measured the bleached halo, pink is unaltered ground mass within the fracture band, and yellow is unaffected magma outside of the fracture band. We see a depletion of 0.8% iron in the bleached zones and a very slight depletion of iron in the pink zones compared to the unaffected magma. Scaling all of the elements to fit on an isocon plot, we can compare the elements in the pink and blue zones to the unaffected yellow zones. On the left, the unaltered pink zones align close to a 1-to-1 ratio, indicating a very little change in composition from the yellow zones. The bleached zones on the right, however, show an enrichment in lanthanum, yttrium, cerium, and chromium, and a depletion in lead, nickel, and iron. Our working hypothesis is this. In the magmatic stage, fractures opened and the pressure drop drew in incompatible elements via volatile fluids. The first elements to precipitate were iron, magnesium, and rare earths. The chemistry of the carrier fluid changed and deposited carbonates. Meanwhile, fractures initiated nearby. Joining of fractures created another sudden pressure change, disturbing the precipitants and reworking them into rounded clasts that were forced into the tips. Precipitation continued until there was nothing left. Although the compositional change caused by each fracture is very small, the compounded effect of the total number of fractures in the entire laccolith would affect the overall composition in a big way. There is no evidence of hydrothermal alteration in the Sandfell system, which is likely the reason these features were preserved. They would otherwise be overprinted in more hydrous conditions. In summary and conclusion, we found a preserved magmatic fracture system with little to no connectivity, and discovered their fillings are enriched in elements which are typically immobile. Our chemical and textural analyses suggest the fillings are primary magmatic features. And the lack of water at the Sandfell laccolith may be the reason the fractures were preserved and their contents trapped in place, rather than carried off into the crust. We may have found a snapshot of the element extraction process. Please feel free to contact me to discuss this further. Thank you.